I'm happy to introduce Professor Fukaya. He graduated from University of Tokyo in 1982, and he made several fundamental discoveries in Riemannian geometry, gauge theory before moving to symplectic geometry. One of his most famous contributions there is joint proof with Kaoru Ono of Arnold conjecture, and one of the main subjects of in symplectic geometry theory Lagrangian intersection, and Professor Fukaya invested enormous time and thought in understanding of this theory, and in particular, he introduced certain algebraic structure called A infinity category of Lagrangian manifold, and now commonly referred as Fukaya category. And this is an extremely important subject, not only in symplectic geometry, but also in mirror symmetry. And most recently, jointly with Ono, Ohta, and Oh, he wrote extremely comprehensive book on Lagrangian intersection theory, and he'll speak about this today.
So, thank you very much for Yasha for introductions. So, I want to talk about Lagrangian Floer theory, and most of the things I talk with joint work with Ohta Ono, and also there are many contributions with many other people. And Floer homology is a subject which is invented by Andreas Floer something like 25 years ago. And it is, in general, a kind of homology theory of degree half infinity and infinite dimensional spaces. And so far, all cases people use Morse theory on infinite dimensional space to realize Floer theory. And there are many examples of Floer theory. I can count at least 6 here. And this Floer theory in general in 2 categories. One is either gauge theory or something low-dimensional topology. And this version of Floer homology associates a group to 3 manifold. And the first example of such a thing is invented by Floer himself. It's in Yang-Mills gauge theory, which associates some Floer group to 3 manifolds. And then after the invention of the Seiberg-Witten theory, then there are new versions, the Seiberg-Witten Floer theory. And Osbach and Sabo, maybe this spelling is not correct, I'm sorry, invent some new version of this Seiberg-Witten type Floer theory called Hegel Floer theory homology. And these 3 are somehow very much important in low-dimensional topology. But actually, the emphasis of my talk is not on this gauge theory side, it's the symplectic geometry side. In the symplectic geometry, we have at least 3 versions of Floer type theories. One is Floer theory of periodic Hamiltonian system, and the other is a Lagrangian submanifold, and the third is a version of a contact manifold, which is Ehrensberg-Hofer-Gibenthal is now developing. And I will explain these 2 more soon. And there are many variants, and actually these 2 are also interrelated. So there are many Floer theories which are related to each other. But today, I want to concentrate symplectic Floer theory. And the symplectic Floer theory has at least 2 versions. We forget contact versions. We have 2 versions. One is a version of periodic Hamiltonian systems. For this Floer theory of periodic Hamiltonian systems, we consider Hamiltonian H, which is a S1 parameterized family of functions on M. And we consider this equation, this is very famous equations of Hamilton in classical mechanics. And we consider a loop from S1 to M, which satisfy these ordinary differential equations. And to understand this periodic solution of this ordinary differential equation is a kind of very basic problem in dynamical systems, Hamiltonian dynamics. And the Floer's chain complex, in this case, is a space of solutions of this periodic Hamiltonian systems. And then Floer introduced some boundary operator for this chain complex. So as a vector space, it is generated by the solution of this periodic Hamiltonian systems. And he defined boundary operator, and he counts this kind of objects. So you have L1, you have L2, and both are solution of this periodic Hamiltonian systems. And Floer considered a map U, which is from cylinder to M. And you assume that the cylinder is asymptotic to L1 when tau goes to minus infinity and is asymptotic to L2 when tau goes to plus infinity. And we put this partial differential equations. And this XH is a Hamiltonian vector field, and J is a complex structures. And in case you have a symplectic manifold, you can associate this complex structure J in a kind of compatible ways. If you do not know so many, then you can just regard M as a Kähler manifold. Then J is a complex structure, and the omega is a Kähler form. But anyway, we count this kind of configurations on two-dimensional objects, and then by counting Fourier-defined boundary operator, and you have generated boundary operator. So this is a Fourier homology for periodic Hamiltonian systems. Then we go to very similar, but it's a slightly different Lagrangian submanifold version. Actually, Fourier studied Lagrangian submanifold Fourier homology. The first Fourier homology, Fourier invented this Lagrangian submanifold versions. And he then generalized this periodic Hamiltonian system and to gauge theory. And in these versions, we consider two Lagrangian submanifold. Let me remind you, Lagrangian submanifold is a half-dimensional manifold of a symplectic manifold. A symplectic manifold has a two form, and the top power is a volume form. And we assume that this symplectic form is 0. So this is a Lagrangian submanifold. And in this version of Fourier homology, the chain complex is, as a vector space is generated by the intersection points. In general, maybe if this intersection is not transversal, then we need to do some other things. But in a simplest case, we just consider intersection point as a generator of Fourier's chain complex. And then we define boundary operator. And the boundary operator is a solution of this differential equations. It's an equation that U is a holomorphic. So U is a map from real line times interval to our symplectic manifold M. So then we assume that when tau goes to minus infinity, it goes to the first intersection point. When tau goes to plus infinity, it goes to the second intersection point. And this part lies on L1, and this part lies on L2. So in total, you have this picture. And we count these pictures, and then this is basically the boundary operator. So that's this idea of the Fourier homology. So let me summarize the stories explained. In a symplectic manifold, we have typical two versions of Fourier homology. One is one periodic Hamiltonian systems, where the generator is a solution of this periodic Hamiltonian systems, and the boundary operator is this partial differential equations. And in a Lagrangian submanifold, you have a pair of Lagrangian submanifold. You consider a vector space generated by intersection points, and the boundary operator is counted by these strips. And of course, Fourier homology is just a kernel of this boundary operator divided by image, and also the kernel divided by image. However, there is some difference. So they too looks very similar story, but there is some difference between these two stories. In the case of Fourier homology of periodic Hamiltonian systems, so one nice feature is that we can define this Fourier homology for arbitrary symplectic manifold and arbitrary Hamiltonian vector field. And then the Fourier homology actually is isomorphic to the ordinary cohomology of M, in case M is compact. So as an invariant, maybe this is not new. But if you know that this is this, then you can get something about the solution of periodic Hamiltonian systems. So this gives some results. And on the other hand, in the case of Lagrangian submanifold, Fourier homology has two different features. This Fourier homology may or may not exist. So it doesn't exist in complete generality. And also, the Fourier homology may not be isomorphic to the homology of the manifold L. So the invariant is more interesting, but if you try to apply it, we need to work harder. So I want to explain these 2 points more. So to explain this, let me somehow say what is the ideal statement for Fourier homology of the pairs. So we expect that if you have a pair of Lagrangian submanifold, then we can associate some group invariant, which we call Fourier homology group. Then to relate this to the intersection of Lagrangian submanifold, it is this second property. If L1 is transversal to L2, then the number of intersection is bigger than the number of Fourier homology. So this means that if you have a non-trivial Fourier homology, these two should intersect, and you can estimate the number of intersection points using Fourier homology. And the third, let me skip third and I'll go back. The fourth is in the case both Lagrangian submanifold is the same, then the Floer homology is expected to be equal to the ordinary homology of your Lagrangian submanifold. And the third is an invariance of Hamiltonian diffeomorphism. Let me explain what is Hamiltonian diffeomorphism. Hamiltonian diffeomorphism is a particular simplex diffeomorphism. It is generated by some h. It's a time-dependent functions on M. And then we consider this famous canonical equation by Hamilton's. So this is the equation for the arc from 0, 1 to M. And we write L to this P and Q in the usual very well-known canonical coordinate in simplex geometry or Hamilton, double coordinates. Then you've got this very famous equations. And then X goes to phi h of X. And X is a starting point of these solutions, and L1 is phi h of X is the ending point of these solutions. So this is what Hamiltonian diffeomorphism. Maybe it is to understand how this definition of Hamiltonian diffeomorphism is related to other things. So let me consider what is the intersections of L1 moved by Hamiltonian diffeomorphism and L2. So I want to consider this intersection points. So this is a kind of Lagrangian intersection theory. And this intersection theory is related to a very famous, very classical problem in Hamiltonian dynamics. We consider these equations of Hamilton's equations, and we require the beginning point lies on L1, and the ending point lies on L2. So the situation is something like this. You have L1 here, you have L2 here, and you consider arc, which start from L1 and end up L2, and satisfies this Hamilton's equations. And we can just easily see that this solution corresponds one-to-one to the intersection of these two Lagrangian submanifold. So the counting intersection of these two Lagrangian submanifold is just to counting the solution of this Hamilton systems. And in a very simple classical example, we take a cotangent bundle. It's a famous symplectic manifold, and L1 is a cotangent fiber of some point P, and L2 is a cotangent fiber of some Q. I'm sorry, this P and Q has nothing with this P and Q. It's just 2 points. So you take two different cotangent fiber. Then this equation says that at time 0, your position is some point, and at the time 1, your position is somewhere else, and you see whether you have a solution of this Hamiltonian equations satisfying these boundary conditions. That's very classical problem of Hamilton dynamics. And so you want to find count the number of solutions, and just count the intersection of these two Lagrangian submanifolds. So let me go back to the story. I'm sorry. Now we have this 4 ideal property which we want to prove. And in particular, if you can prove these things, then we know the number of solutions have some Hamilton dynamics using this homology groups. So that's somehow one of the big motivations of Floer theory to be invented. And Floer, maybe it's 70s, I'm not so much sure, 80s, invented this Floer homology theory. And as I said, that this Floer theory for Lagrangian submanifold is rather more complicated than the than the case of periodic Hamiltonian systems. In the first case Floer studied, in the case when this relative second homotopy group is trivial. And this is actually rather restrictive assumptions, but still it's very interesting to work this out. And then Floer proved this all 4 properties I just listed up in this particular case. And then after Floer did this Y.G Oh came up, and he relaxed this strong condition to this monotone conditions, plus something about the Maslov index. So the Floer homology can be defined in bigger generality. And Y.G proved this first 3 properties of this Floer homology to be expected. First 3 is what? Yeah, so this well-definedness, estimate of intersections, and invariance. But then Floer homology actually is not isomorphic, and Y.G observed that the Floer homology is not isomorphic to the ordinary homology. So it is in a kind of almost 20 years ago. Then I want to explain why this Floer homology. So I want to explain this point, that this kind of Floer homology, which satisfies all the property, actually does not exist. And we can see in the following way. first we assume that we have a Floer theory which satisfies all 4 properties. And then we can prove that if such a Floer theory exists, then for any Hamiltonian diffeomorphism phi, intersection number between L and phi of L is not smaller than the Bethe number. This is good theorems, except it is not correct. So the proof is easy, so I want to explain how to prove this from these 4 properties. So suppose you have this intersection point, then we have this inequality 2. Inequality 2 means that this number of intersection is bigger than the Floer homology. So we just apply this, we have this part of the inequalities. Then we use this property 4. If both Lagrangian submanifold is L, then the Floer homology is a homology group. And maybe we need also this property 3, that the Floer homology is invariant of Hamiltonian diffeomorphism. So then this one is isomorphic to the ordinal homologies, and this rank is not smaller than this rank. Then in total we get this inequality. So you can estimate the number of intersections by Bethe number. And this inequality is not true, actually. And the counterexample is very easy to cook up. You just consider any compact Lagrangian submanifold in complex vector space. Then you can just move this in one direction, in parallel directions. It is a Hamiltonian diffeomorphism. Then you can just displace L to itself. So you have this number is 0, and this number is positive. So this inequality is not correct. So if you try to prove Floer homology which satisfies all 4 properties, you certainly fail. So you cannot prove it. So this was last century, and then we just worked out for this 10 years what is a good way to somehow modify this story to change the statement to something correct. So necessarily the statement gets more complicated but still useful. And I explained these 4 statements. So there are 4 statements, and they correspond to 1 to 4 from the earlier versions. So let me start from this first property. So the ideal statement we wanted to prove is that we have a pair of Lagrangian submanifold, then we have a Floer homology always. And this is a bit too much to expect. And what we prove is that for so the spin condition is, I don't want to explain so much, but there are some spin Lagrangian submanifold. Then you have some set which we call Molar-Cartan formal scheme, and we can define Floer homology parameterized by this set. So Floer homology has some extra parameter which we call Molar-Cartan formal scheme. So Floer homology does not depend only on Li, but also there's some sets which we call Molar-Cartan scheme. And in this generality we can define Floer homology, but unfortunately this set which I said can be empty. So in the case of this M of L is empty, we cannot do anything. But in many cases we have still this non-trivial set, and we can define Floer homology. We cannot expect everything to fall, so this is something we can do. Maybe best we can do. So this is about the first statement. And the second statement is very much the same. This Floer homology we defined here still bounds the number of intersections from below. So this second is the same. And the third is almost the same. This Floer homology is invariant, but we have to include this Molar-Cartan scheme, and we have a natural map between Molar-Cartan scheme, so that including them, the Floer homology is the same. And the fourth is somehow, again, another difference. So the ideal statement I mentioned is that if this 2 Lagrangian submanifold is just L itself, then the Floer homology is ordinal homology. And we need to define this statement, and then there is some spectral sequence which starts from this ordinal homology and which end up with Floer homology. This means that you have some kind of differentials on this, higher differentials, and there are cancellations, and you end up some HF. Of course, if you just write this, then statement itself is not somehow does not imply so much, because this spectral sequence can be very highly non-trivial, so that this becomes always 0. But we can get some results also by calculating Floer homology. But so this is a kind of general framework. So the framework is as follows. No. So the framework is we define Floer homology parameterized not only by Lagrangian submanifold, but also with some extra parameter which we call Molar-Cartan scheme, and it bounds the intersection number, and it's also invariant by Hamiltonian diffeomorphism, and it is related to the ordinal homology by spectral sequence. So that's the kind of framework, and we have to apply this. But if we are going this, I want to say some algebraic structures. So this statement looks rather complicated, but there is somehow some way to introduce some new algebraic story called the infinity algebra, and we can just reduce this statement to some homotopy theory of infinite algebras. And I want to mention what it is in a few words. So infinity algebra is a kind of generalization of differential graded algebras. And in differential graded algebra, you have a boundary operator, which is M1 in our case, and you have a product, which is M2. And in our situations, we have a series of operators Mk. Actually, k goes from 0 to infinity. So you have infinitely many operators. From k tensor product of your vector space or chain complex to C. So this is infinite algebras, and we have one single requirement for this equation, for this operator to satisfy. It's these equations. It looks a bit complicated, but you just compose this operator twice in an arbitrary way, and you put some signs, and you sum it up. It's 0. So this is called infinity relations. And in the case of differential graded algebras, you have M1 and M2 and no other things. And you can just pack up the conditions that M1 and M2 is a differential graded algebra in this uniform ways. So differential graded algebra is a particular example of infinite algebras. But infinite algebra is more general. So you have this kind of structure. And once you have infinite algebras, we get some equations which I call Mohr-Cartan equations. And you have Mk and b to the tuple k, and if you take sum up, it's 0. This is called Mohr-Cartan equations. In the case of differential graded algebra, this equation is db plus b wedge b is 0. And that's a classical Mohr-Cartan equations. So this is a very simple natural generalization of the Mohr-Cartan equations, and we have a natural notion of gauge equivalence. So we divide it up, we get some sets. That's this M of C, which I wrote before. And then the statement can be summarized into following two forms. If L is a Lagrangian submanifold, which is relatively spin, then its homology group, this ordinary homology group, has a structure of filtered infinite algebras. I think I don't want to explain what is filtered, but it's similar. You have some filtered infinite algebra structures on your homology group, and this structure is well defined up to isomorphism. And if you have a pair of Lagrangian submanifold, then you have two algebras, and you have something called a bimodule, which I don't want to define, but you have a bimodule which is a Floer homology, and this bimodule is well defined. So somehow this series of statements I just wrote before can be cooked up from this algebraic result by purely algebraic method. So the invariant we can associate is a filtered infinite algebra, and for the pair is this bimodule. Actually, we can generalize this to 3 or more Lagrangian submanifold. In that case, we have this kind of triple product structures. So this is a kind of general story of Lagrangian Floer theory, and I want to explain which kind of applications we have. Something is potential, but we already have some applications. And as far as I know, there are 3 kinds of applications of Lagrangian Floer theory. One is somehow Lagrangian intersections, and this is a kind of origin of the whole story. And the other is to have some restrictions of Lagrangian submanifold. This means that if you have a fixed simplex manifold, then we have to know which kind of submanifold can be a Lagrangian submanifold. And we have some information about it. And the third statement is mirror symmetry. So I will explain a few to these 3 things. So Lagrangian intersection Floer theory is, as I explained before, if this ideal case, intersection number can be estimated below by Betti number. So this kind of things is a natural application for this Floer theory to Lagrangian intersections. But as I said, that this doesn't hold in complete generality by this simple example in the case of complex vector space says. So we need to do some modifications. And there is a proposal by Giventhal conjecture, which somehow supposed to be correct, is the following. This estimate of the intersection number by Betti number holds at least if L is a fixed point set of some anti-holomorphic involutions. The simplest important example is if you consider algebraic variety defined over real number, then this L is just a real point of this algebraic variety. If you have any Hamiltonians, then this intersection has this estimate. And this conjecture somehow we wanted to prove, but we couldn't prove it yet. There is various difficulties. And so far, we can prove in the following case that that's something called a spherically positive case. Rather than define what this spherically positive means, that I want to explain this most important case. The first case is the case C1 is proportional to the symplectic form with positive ratio. So it's something like a topological version of Einstein conditions. And the second case is a compressed dimension with 2, and the third case is called Fano. It's another positivity assumptions. Suppose your symplectic manifold is a direct product of one of these three classes, then this is correct. So that we can prove this our version of Floer homology. And this is not yet so much satisfactory, so we have to prove this, but we still could not do it. This is very delicate questions. And the second is a bit more. So let me explain this. Even dimensional cohomology from the ambient space to L is surjective. Then we have this estimate. So this condition that even dimensional cohomology is surjective, I'm not so much sure how much natural. And the other condition is that if this M of L is a Molar-Cartan scheme is non-empty, then this one is estimated by the rank of L minus twice of the kernel of the homology. So this statement is a bit complicated, so I don't want to explain so much, but this uses this force theorem. So force theorem means that you have a spectral sequence from ordinal homology to the Floer homology. And if, of course, if this spectral sequence degenerate, then the Floer homology is equal to the ordinal homology, then you got this estimate. And we want to see how much killing occurs in this spectral sequence, and that's the result of the second statement. So I show this because at least to see that this fourth statement has something non-trivial. So you got this kind of estimate, and we hope we can improve, but in complete generality we cannot do so much. And there is some other results coming from Floer theory or pseudo-homological disk theory. It's about the restrictions of Lagrangian submanifold. And this theorem by Gromov is even earlier than Floer. You have a Lagrangian submanifold, compact Lagrangian submanifold in complex vector space. Then its first cohomology is non-trivial. And Gromov proved a bit more. If you consider this map E, which on the first homology to L, it's just a variation of symplectic form by this disk. Then Gromov proves that this map is non-zero. So this in particular implies this. And see. So, but this result by Gromov is before Floer, and we want to somehow improve this kind of result using Floer homology. Let me mention two terminology. Exact Lagrangian submanifold is this that somehow this all the holomorphic disk this integration of symplectic form is trivial. And there is something called the Maslov class. I'm sorry, this is Z, not R. This is integer. And this is cheating definitions because it's a kind of relative version of C1, but this definition itself does not make sense. That's why I put parentheses, but to define is a bit more complicated, so I just defined. There is some other notion, Maslov class. This is the integer. So, I mean, in symplectic manifold, you have two important two forms. One is symplectic form, and the other is the first Char class. And this exactness is related to this area, and the Maslov class related to the C1. So that's what this 2 means. And this famous conjecture is you have a Lagrangian submanifold in complex vector space. Then this Maslov index is non-zero. I'm sorry, this is Z again. So what Gromov proved is that this E is non-zero, And it is also expected that this Maslow's class is also non-zero. And Biran-Chiribak, we proved it in the case when the second homology vanishes. We use again some kind of Floer homology argument. And the argument this looks like something like this. So we remember that this, if you have a Lagrangian submanifold in complex vector space, then you can isolate this from itself by Hamilton diffeomorphism. This means that there should be something wrong in the Floer theory. And we can use the fact that there should happen something wrong in Floer theory to prove this kind of statement. That's very rough ideas of these two. And in other case, we have a bit more. It's not strictly this Floer theory, but it's very related to Floer theory. If you assume your Lagrangian submanifold is K-pi1 space, it means that all the higher homotopy group vanishes. Then Maslow's index has 2. Moreover, your Lagrangian submanifold has a finite covering, which is homotopy equivalent to S1 cross L prime. So you have very restrictive aspherical manifold, and the Maslow's index is 2. So this is another applications. So this is I explained 2 applications, and the biggest difficulty to apply Lagrangian Floer theory is calculations. So if you calculate Floer homology, you have each time you get applications. But you go back to the proof, if you go back to the definition of Floer homology, then you need to determine all these disks which bounds this Lagrangian submanifold. So definition of Floer homology involves counting of disks. And the disks, equation for disks is a kind of highly nonlinear partial differential equations. And you try to count the solution of nonlinear equations, usually you cannot do it. So calculating Floer homology, Lagrangian Floer homology is always big trouble. It's not only Lagrangian Floer homology, for all versions of Floer theories. Definition is not so easy, but once you finish definitions, then you have to start calculations, and it's always big trouble. And so far, there is 3 related, 3 methods to calculate Lagrangian Floer theory. I want to explain them quite a bit. And the first one is reduction to Moss theory. So I think this is invented by Floer himself. So this goes in the following way. Suppose you have 2 Lagrangian submanifold in a symplectic manifold, and assume that second L2 is very close to L1, maybe in C1 sense. Then there is so-called symplectic neighborhood theorem by Weinstein. This L2, in a sense, can be regarded as in cotangent boundary of L1. So you have L1, its neighborhood is like a cotangent boundaries, and L2 is very close to L1. And then in the cotangent boundary, it can be regarded as a kind of graph of closed one form. So L2 is a closed one form, and what Floer discovered, if this closed one form is exact, so it's a D of some function f, then Floer says that this Floer homology between these 2 Lagrangian submanifolds is a so-called Moss homology of L. It's actually ordinal homology of the manifold. And the idea is somehow you have this guy. So this horizontal line is 0 sections, and this curved one is a graph of D of f. And we consider this pink disks. I'm sorry, this white part is because of my computer skill. I don't know how to fill this. So you have this kind of disks, and you want to count this kind of disks. Then what Floer found that this kind of disk is equal, it can be identified with a gradient line. This purple point is a critical point of f, and you consider gradient vector fields and the integration gradient curve, which goes to from one critical point and the other critical point. And this kind of gradient curve can be identified, can have one-to-one correspondence to these disks. That's what Floer proved in the 1980s. And this is the way Floer calculates some Floer homologies. And this works in some favorite case, and in the case where L2 is very close to L1. And then later on, with Y.G Oh, we generalized this Floer story quite a bit to this, including this higher product. So let me remind you, M1 is just a boundary operator, and in the case of M1, Floer relates this Moss theory and Floer homology. And we consider this triangle, and this triangle counts this M2 actually. This is a holomorphic triangle, it's very narrow. And what we proved is in some favorite case, like cotangent boundaries, then this triangle turned out to be the solution of this three-like configurations of gradient lines. So this is a kind of way we can study. And this story continues. And so we did it in the kind of 1990s, and in a famous paper 2000, Concept-Soberman found that this, so we did it for the cotangent bundles, but we can do it for the Tn bundle over some manifold. And this generalization is important because mirror symmetry, we have some kind of Lagrangian torus fibrations, and Concept-Soberman found that this kind of degenerations business you can do for the torus bundles. And after that, there are many, some other progress that we can just include singular fiber, not a bundle, but singular fibrations. And also here, we just have a strip, but we can also do this kind of cylinder. And actually, this story in the case of cylinder is very much related to this. Actually, in a sense, the same as what people are working on tropical geometry. So these two stories somehow joined at some point in early 2000s. And this made more progress in 2000. So I want to explain another technique to study, to calculate Lagrangian Floer theory. That's cutting and pasting. And as far as Lagrangian Floer theory concerns, this cutting and pasting is still very much primitive stage, but we can do something. So the problem is, suppose you have a 3 Lagrangian submanifold in M, and you assume 2 of Lagrangian submanifold intersects transversally at one point. Then we can just take something called Lagrangian surgery. It is diffeomorphic to the connected sum. Then, so maybe figure is better to see, right? So you have this configuration. You have 3 Lagrangian submanifold, L1, L2, and L3. And this yellow point is just transversal intersections of L1 and L2. Then we just deform this L1, L2 a bit here on this intersection points, and you get this configurations. This is called Lagrangian surgery. Topologically, it is a collected sum. Then we want to calculate these two gongs. So you have another Lagrangian submanifold L3, and you have these disks. And these two pink dot is the generator of this Lagrangian Floer theory, and you want to calculate these two gongs. And these two gongs determine the boundary operator to calculate this Floer homology. On the other hand, we have this triangle. You have two pink dot and one yellow dot. We construct this holomorphic triangle. And actually, this holomorphic triangle calculates this product structure among 3 Lagrangian submanifold and 3 Floer homologies. And what we proved is that this triangle and these two gongs are somehow related to each other. It depends on this kind of sign of these epsilons. In a case when epsilon is positive, then this triangle corresponds 1-to-1 to these two gongs. In the case epsilon is negative, this triangle corresponds to Sn-2 parameterized family of two gongs. So once we know how many triangles, we know how many two gongs. So that's kind of analysis. So we can work out some kind of analytic problems, and then we get we can reduce the calculation of this two gon to 3 gons. So that's this story. So let me so that boundary operator of this Floer homology of the collected sum or Lagrangian surgery is related to the product structure among 3 Floer homologies. So if we know one of them, then we can calculate other of them. And of course, to calculate each of them is not so easy. But in some simple case, we can calculate this side. Like in the case L1, L2, L3 is very simple, like a linear subspace in CM. Then we can calculate this, then we can use it to calculate this in some particular case. And I believe that this statement about cutting and pasting is very much primitive. So it's just the case of collected sum. But I don't know what's a good way to generalize it somehow. The problem is hard to state. So probably one should develop more this cutting and pasting techniques to calculate more Floer homology. But this is just the beginning. And we can calculate several examples by using this cutting and pasting technique. And the biggest, the most somehow interesting and the most promising approach is to use homological mirror symmetry. And this idea of homological mirror symmetry is invented by Maxim Kontsevich in 1994 in a talk at the International Congress at Zurich. And it's a kind of a very important version of mirror symmetry, which is discovered a bit earlier by physicists. And in this version, Kontsevich studied the following things. One is a symplectic manifold. And the mirror symmetry predicts that there is some complex manifold which associates to symplectic manifold. And we consider a pair of Lagrangian submanifold L on symplectic manifold and B B is an element of M of L. Let me recall that M of L is a kind of so-called molar Cartan scheme which parameterizes the Floer homology. So you have this pair. So this kind of data we need to define Floer homology. Then the mirror should be some holomorphic vector bundles. This is a bit too much. It's a kind of a chain complex of holomorphic vector bundles, or better to say, object of derived category of covariance sheaf. So this is the kind of mirror side. And then if you consider a pair of this kind of object, they have a Floer homology, and then you have extensions. You have a sheaf cohomology, its extensions. In the case of just a vector bundle, you take a home bundle and take a D-bar cohomology. So you have this cohomology group. And what this homological mirror symmetry conjecture that this Floer homology is isomorphic to the sheaf homology, and actually this isomorphism is factorial. So there are many reasons to study this homological mirror symmetry, but for me, the biggest motivation is to apply this for calculations. I mean, we have this isomorphism, conjectured isomorphism, and then if you see that the sheaf cohomology, I don't know how people feel sheaf cohomology is hard to calculate, but I'm pretty sure that sheaf cohomology is easier to calculate than Floer homology. Complex geometry has a long history, so people established technology of sheaf cohomology. So in principle, if you are given sheaf, you can calculate cohomology in finite amount of time, I think. And that's not true in Floer homology. If you have a given Lagrangian submanifold, then usually you can never calculate Floer homology. So if you know that this is isomorphic, then you can reduce the calculation of Floer homology to the calculation of sheaf homology. So that's one good thing. Actually, this coincides with one of the main motivations of physicists to start mirror symmetry. In physics, I mean, you have homological mirror symmetry. So physicists try to calculate Gromov-Witte invariant of some simplex manifold, and the Gromov-Witte invariant count homologic map from spheres. This is nonlinear problem. It's hard to calculate. Then this homological mirror symmetry says that this nonlinear problem turned out to be equal to some problem about the product structure in a sheaf cohomology, and the product structure of sheaf cohomology is a kind of linear problem, and is a kind of local sheaf cohomology can be calculated. So, and this is a way that Candelas and those people calculate the number of rational curve in quintics. So we want to imitate this kind of calculations. So try to use this Floer homology to calculate, try to use sheaf cohomology to calculate Floer homology. And let me remind you that if you can calculate Floer homology, you can somehow estimate the number of solutions of some Hamilton dynamics. So you use sheaf cohomology to calculate the number of solutions of Hamilton dynamics. That's something I think is very, very interesting to do. But of course, if you want to use homological mirror symmetry for this kind of purpose, we need to prove it. And that's somehow another big problem. But fortunately, recently there are many examples we can actually prove this homological mirror symmetry, at least partially. I mean, 10 years ago, this list is almost empty, but now we have many examples. And the first case that this homological mirror symmetry is proved by in the case of elliptic curve. And this is actually the case when Kontsevich studied, and it led him to make this conjecture. But even in the elliptic curve case, this is a very interesting phenomenon already occurs. And the Polistic and Jastrow somehow studied more on the elliptic curve case, and in the elliptic curve case, we understand almost everything now. Then the next case, you can make a bit higher dimensions, so you have a tori of higher dimensions. And I proved it in partially in 98, and also Kontsevich Soberman gave a different argument. And that's a kind of case when Lagrangian submanifold is linear or flat. You have a tori, and you have a flat Lagrangian submanifold. And that looks like a simple case, but still, even in this flat case, it's highly non-trivial, and we can prove homological mirror symmetry in that case. And I think last year, there are a paper by Mohamed Abusai and Ivan Smith. I'm sorry, this is Smith. And they established in the T4 case incomplete generality. And now, somehow, we almost understand all the stuff we need to prove it in complete generality for the tori. But actually, the story is rather heavy to write up, so nobody yet write it up. But I think it's a kind of problem of writing, but maybe we need several hundreds to write it. So, but still, at least on the tori case, we can prove it. And this is the quadratic. I don't know this spelling is correct. It's a kind of degree 4 algebraic surface in P3. In the case of this degree 4 surface in P3, Paul Zeider proved it in 2003. And then there's a Paul-Zeidel's proof is somehow different from the techniques I explained, any of the techniques I explained here. He used some kind of symplectic version of Lefschetz special techniques, which I don't have time to explain, but they're very interesting ideas. And then there's another case of homological mirror symmetry that's called the Landau-Ginzburg fan over toric mirror. And I don't have so much time to explain, but in the case of this, there are two cases. One is a toric. As I said, that mirror symmetry is symmetry between symplectic manifold and complex manifold. And the toric manifold, it can be either complex or symplectic side. And the Landau-Ginzburg model is a kind of, in this context, is a kind of a singularity theory. And you have a singularity, you can consider singularity theory either in symplectic side or the complex side. So the one version is you put toric manifold in complex side and the Landau-Ginzburg model in symplectic side. And this version is studied by Uru, Bondau, Katsarkov, Ueda, and Upside, and other people. And we have many cases that this is proved. And there is another case that you put toric manifold, you consider toric manifold as a symplectic manifold, and this singularity theory as a complex manifold. Then we have this Oh's result, and after that, with Ohta Ono, we are working on this case, and it's somehow rather a big case. We can prove it. And there is another case. It's a cotangent bundle. It's one of the classical case of symplectic manifold. And in this case, what is the complex side is not so clear, not so much very clear. But in the complex side, of course, the cotangent bundle is not so good complex manifold. But then you say flat vector bundle instead of holomorphic line bundle or something like holomorphic vector bundle or something like that. And this version, in some cases, is proved in some way proved by Nadler Zaslow and Seidel Smith and myself. And there is a paper by Seidel on this genus 2 surface. And now I believe that in a K3 surface, it's very similar to this case. But we have, I think there is I know this how to, I now have all the integrants to work out this case. But still, it's in progress because the total amount of writing looks rather heavy. So that's the case that homological mirror symmetry is proved. And I feel that this list is now beginning to blow up. And so somehow in the near future, maybe if homology changes to something which we can never calculate or something which we can calculate and use. That's something I hope. Okay, I stop here. Thank you very much.